What new experiments and technologies might finally solve the universe's biggest missing puzzle? Right now, a global army of scientists is deploying the most sophisticated detection equipment ever created in a high-stakes hunt for dark matter and dark energy. These experiments represent humanity's greatest effort to understand the 95% of the universe that remains invisible to our instruments. The search for dark matter has entered an exciting new phase. After decades of increasingly sensitive experiments coming up empty, scientists are expanding their approach beyond the traditional WIMP hypothesis. The XENONnT experiment in Italy's Gran Sasso Underground Laboratory represents the current state of the art in conventional dark matter searches. This detector contains over 8 tons of ultra-pure liquid xenon, making it about 3 times larger than its predecessor. Its remarkable ability to reject background radiation allows it to distinguish between genuine dark matter signals and constant bombardment from other particles like neutrons or gamma rays. While XENONnT looks for direct particle collisions, the ADMX experiment at the University of Washington hunts for axions, a completely different dark matter candidate. ADMX functions like a radio receiver tuned to detect frequencies where axions might convert into photons within a magnetic field. By exploring territory conventional detectors can't reach, ADMX could potentially find particles thousands of times lighter than previously searched for. Directional detectors represent another innovative approach. Experiments like DRIFT in the UK and DMT-PC in the US aim to determine which direction dark matter particles come from. As Earth moves through the galaxy's dark matter halo, these detectors track tiny recoils of atoms struck by particles, preserving directional information. This approach could provide the smoking gun evidence needed to confirm a dark matter detection. Dark energy research requires entirely different methods. Since dark energy appears to be a property of space itself, scientists must map its effects across cosmic distances. Major space missions are transforming our understanding of cosmic acceleration. The European Space Agency's Euclid mission, launched in July 2023, is the first space telescope specifically designed to study dark energy. Euclid will measure shapes and redshifts of billions of galaxies spanning 10 billion years of cosmic history. Its revolutionary capacity to measure both expansion rates and cosmic structure growth provides 2 independent ways to track dark energy's influence. NASA's Nancy Grace Roman Space Telescope will launch later this decade with even more powerful capabilities. Its wide-field instrument will cover an area 100 times larger than Hubble with similar image quality, detecting subtle gravitational lensing effects across vast cosmic distances. Roman will determine whether dark energy strength has changed over time, a critical question for understanding its fundamental nature. Ground-based projects like the Dark Energy Spectroscopic Instrument, DESI, are making equally impressive strides. Operating since 2021, DESI will eventually measure precise 3-dimensional positions of 40 million galaxies using robotically positioned optical fibers. This will create the largest and most detailed 3D map of the universe ever made, revealing crucial constraints on dark energy models. These cutting-edge experiments harness revolutionary advances in quantum technology. Quantum sensors enable measurements at the very limits allowed by quantum mechanics. The Magus 100 experiment under construction at Fermilab uses atom interferometry, a technique treating atoms as waves, to search for ultralight dark matter and possibly gravitational waves. These methods can detect tiny forces that would have been undetectable just a decade ago. Quantum computing promises to revolutionize data analysis for these massive datasets. Where conventional computers struggle with complex simulations of dark matter distribution or extracting subtle signals from noisy data, quantum computers could perform these calculations exponentially faster, allowing scientists to test many more theoretical models. What makes modern research particularly promising is its interdisciplinary approach. The boundary between astronomy and particle physics has blurred. Particle accelerators probe matter's smallest scales, while astronomical observations reveal the universe's largest structures. Both provide complementary information about dark matter and dark energy. Early results from ongoing missions offer tantalizing clues. The Gaia space mission has created unprecedented maps of our Milky Way, revealing subtle irregularities in stellar motions that could indicate dark matter substructures. The South Pole Telescope has observed patterns in the cosmic microwave background suggesting possible deviations from the simplest dark energy models. The international scientific community shares a profound hope that these tools will finally illuminate the cosmic shadows. Thousands of researchers across continents work tirelessly, united by the common goal of solving these fundamental mysteries. What if these breakthroughs are just the beginning of a complete transformation in our understanding of physical reality? These massive scientific efforts reveal something profound about human knowledge. We have developed the capacity to know what we don't know, to precisely measure our cosmic ignorance. This knowledge of our limitations represents a triumph of the scientific approach, driving us to develop ever more ingenious methods to probe the unknown. What might these cosmic mysteries ultimately tell us about science and human knowledge? Perhaps that our greatest discoveries often begin with our greatest puzzles. The greatest mysteries in science have always led to our most profound discoveries. Dark matter and dark energy aren't failures of scientific understanding. They're opportunities that could completely transform how we see reality. These mysteries push us to develop new technologies, new theories, and entirely new ways of thinking about the universe. What strikes me most is that humans, tiny beings on a small planet, have measured something we can't see or touch. We've glimpsed the cosmic unknown from our modest corner of existence. We stand at the threshold of discovery, poised to rethink not just our scientific models, but our very